All right. Hey, everybody. Today we're going to talk about statistical distributions, topic 12 in our phase 2 curriculum. So last time we talked about probability, and today we kick off I think the first of 12, 13, 14, 15, 16. The first of 5 stats topics. I also want to reiterate that the labs for these topics, there is a good bit of coding involved. I think a lot of them have you code out the statistical formulas. Again, want to reiterate, they make you do that, and then probably at the end, they give you like the built-in method, and you probably will never have to hard code these statistical methods. For this, I really do think that it is good enough to understand overall concepts. So just to plug this again, there is a document here where I'll refer back to this doc over the course of this course, but these are the statistics questions that are good to remember. Or if you want to have like a little checklist of what concepts do you have to remember, maybe like copy this doc and then answer these questions as we get to each of them. Like I think today we're going to hit what's a probability density function, what is a normal distribution. So these are what we're going to talk about today. And then the rest we're going to hit over the next couple of weeks. So again, the coding for this less important. It's really just how you interpret statistics. All right. So today we're going to talk about expected values and variances. We're going to talk about PMF, PDFs, and CDFs. Those which I will talk about, and I'll explain what these stand for later. We're going to talk very briefly about Bernoulli and binomial distributions. These are just different kinds of discrete distributions. Again, I know a lot of technical words, but we'll explain it more later. Normal distributions, and we'll start to set up what a z-test means. All right, so let's talk about expected value and variance. So in terms of definition, any random variable, and what I mean by random variable is just anything that can have a random outcome. So if you think about flipping a coin, the result of flipping a coin is actually a random variable as well, where there's a 50% chance of getting heads, 50% chance of getting tails. So the outcome of flipping a coin is a random variable because it's not, you don't definitely know what the result is at that moment. Same for like rolling a dice. The outcome of a dice roll, also a random variable. So here's some formulas, not important to remember. I think these are actually built into not NumPy, but SciPy, SCIPY. If not, it might be in NumPy as well. I forget right now. But every random variable has an expected value and a variance. And for specific named distributions, so today we're going to talk about Bernoulli, binomial, and normal distribution. There are often formulas for expected value and variance that simplify these forms, because this I know looks a little bit intimidating. So expected value, several ways that you can sort of think about it. It is the sum of the value times its probability. So if you see this like E looking symbol, it's actually sigma. This is the probability of an outcome multiplied by the outcome itself. So as an example, for the heads and tails problem, let's just say 0 is tails, 1 is heads. So the way that you will calculate the expected value for a coin toss, and let me draw it out here, would be the sum of the probability. So there are 2 outcomes for a coin toss, the head outcome, and then there's also the tails outcome here. And we're multiplying the probability of the outcome by the outcome itself. So probability of the outcome of heads is half, same for tails. And then we're going to multiply it by the outcome itself. And then we said that heads is going to be 1, tails is going to be 0. And so the expected value of a coin toss is actually 0.5. So other ways to think of it, it's sort of like an average. You might think of it as an average. Some people like to think of it as like the best estimate of the mean value or something like that. So kind of similar. If we look at the example of a dice roll, you have your values of 1 through 6. And then if we were to do the same thing for a dice roll, but with like 1, 6 times 1, so on and so forth for all the different values. And let's see, 1 over 6, oops, 1 over 6 times 6, so on and so forth. You'll see that the expected value for a dice roll for a 6-sided die is actually going to be 3.5, which in this case, because each probability for each outcome is the same, 3.5 happens to be right in the middle of all of the values. If you have like a weighted die, let's say like 6s happen to be like the dice is weighted to roll 6s more often, you'll see that this expected value will go up. So roughly that's what an expected value is. And this formula, as long as you can figure out what your discrete or your specific outcomes are, you can actually calculate an expected value for any random variable. A little bit more abstract is variance. So variance basically tells you what does the spread of values look like? How varied can the values be? And the formula is a little bit more complicated. Here we have the probability of the outcome, but here we have the difference between the outcome itself and the expected value squared. So let's use the dice roll example because that is easier. Let me just erase this for now. So let's use the coin toss example. So we found the expected value here. The expected value is 0.5. Let's work out this formula real quick. So here we have the sum of the probability of the outcome multiplied by the value itself minus expected value squared. So 1 minus 0.5 squared, and then plus 1/2 again. This is for, and this is for heads. And then here we have 1/2 times 0 minus 0.5 squared. And I forget what this evaluates to. I think this is what, 0.25. And then this is also 0.25. And then half plus half, I think it comes out to 0.25. I don't want to do the exact math now, but if you evaluate this, that will be the variance of your random variable. And we'll see in a little bit when we get to the Bernoulli and the binomial distributions, these will be easier to calculate than writing all of these formulas out. Why these are important, the expected value and variance, these are two of the summary statistics that really help to define the nature of a distribution, right? If you can figure out the average value and roughly the spread of values, it can tell you a lot about how a random variable or a set of values is distributed. So if you remember, I think when you do like df dot describe, it does give you expected value and variance of your numerical columns. All right. Next, we're going to talk about probability mass function, which is the first of these three acronyms. So probability mass function is just a function that shows you the associated probabilities with discrete random variables. So for this case, let's just imagine that this is just some 5-sided dice. This is just some 5-sided dice, and these are the probabilities of each outcome. So when we have a probability mass function, and we're going to compare this in a bit to a probability density function, important to know that mass function is for discrete variables, density function is for continuous variables. Now, the difference between discrete and continuous, if it's discrete, you know that there are specific values that the outcome can have. So in this case, this random 5-sided die, it can only be 1, 2, 3, 4, 5. It cannot have values in between. To contrast, something like temperature. So this is temperature on June 1st in New York City. This is just a distribution, I guess, of all the historical June 1st temperatures. The temperature can be any value between the range of like, I guess, 70 through 90 roughly. So that's a big difference between a discrete random variable and a continuous random variable. So for discrete, we have a probability mass function. In a probability mass function, a few things to remember. This is our sample set. And so therefore, all of these probabilities have to add up to 1. So here you can see like 0.3 something and like 0.15, what's this, 0.08 and 0.15. These will all add up to 1. And you can actually find the expected value and variance of this random like weighted 5-sided die by using the same formulas that we used here. So I will say that for data science, probability mass functions are not used as much as density functions because a lot of the variables that we use in data science are continuous, but this is a simpler example to go off of. Main thing to remember is it just shows the distribution of probabilities for outcomes, and all the probabilities have to add up to 1. So to contrast, we have probability density function now. So instead of having discrete, outcomes, like it's not just 70, 75, 80, 85, 90, temperature can be any value between 70 and 90. And you can even get like into the decimal points, and you can get very, very granular with these values. Therefore, it is continuous. So because it's continuous, it's more of a curve shape rather than a series of separate bars. So therefore, the probability here is associated with a curve. It's actually very, very similar the way that you read this versus the way that you read this. If you have, and let me grab something to draw a line with. All right, so let's just say like what is the probability of the temperature being 75? You would draw a line up from 75 and then look at it here. Okay, the probability is roughly like 0.035. Let's look at the probability of it being 80. So this is just estimating. So the probability of it being 80 is going to be around, what's this, 0.13. So you read it very, very similarly as you do with a probability mass function. So for continuous random variables, if you think about it, where in the case of the probability mass function, all the values have to add up to 1. In a probability density function, rather than the specific values adding up to 1, what you have is the entire area under the curve has to add up to 1. This gets into a little bit more complicated with like calculus and integration. But basically, if you look at this area under the curve, if this is like roughly 0.13, and if you were to estimate the area under this curve here, something like this, all of these bars will roughly add up to 1. So the main thing to know here is that to compare to the mass function example, in a probability density function, the area under the curve, which is this green shaded area that I'm shading right now, area under the curve is equal to 1. So with that, usually with a continuous random variable, you find the probability of a range of values. So for example, let's just say that we're looking at the range from 79.3 and 80.8, which happens to be this middle bar over here. So with this middle bar over here, you'll look and see where this estimates to. This estimates to about, let's just say that's about 0.13. So that's why we have 13% of the time, you'll observe a temperature between 79.3 and 80.8. These are just little things to remember with probability density function. The main definition that you have to remember is it just represents the distribution of probability of this continuous random variable, which in this case is just the temperature on June 1st in New York City. Any questions about this? All right. So next up, something to just add on to the probability density function, we have a cumulative distribution function. This one's a little bit less common, but cumulative distribution function can be for both discrete or continuous variables. And what it does is it just looks at probabilities in a cumulative way. So in the example of a dice roll, instead of having, I guess in this case, instead of having 6 bars that just go straight across, oops, I want to draw some bars. Instead of having straight bars that go across from like 1 through 6 at the same probability, this measures the probability that X is less than or equal to a certain value. So that means what this staircase looking thing is showing you is that, let me just clear this again, is let's say we're looking at the dice roll for number 4 over here, which I think will evaluate to about 0.66. So 0.66 is the probability that your dice roll will be 4 or smaller. So that x is less than or equal to the number 4. That's what a cumulative distribution function shows you. Sometimes it's helpful, especially if you want to know, like, okay, what's the probability of anything leading up to a certain value? It's very, very similar for the continuous example. So instead of it being like a bell-shaped curve, like what we had for the temperatures of the previous slide, it actually adds up. So if we look at this value over here, what's the probability of a temperature being below 85 degrees? Below 85 degrees had a probability of about, like, I don't know, 0.9 something. And what's the probability of it being below 100 degrees? Pretty much 1. So the temperature is always below 100 degrees. So cumulative distribution function is a little bit less common, but can sometimes be very, very useful. So that's good to know. All right. Next, we'll talk about some of these named distributions I was talking about before. And these might actually sound, after we describe these distributions, you can actually apply them to a lot of things that we see and experience in our daily lives, but they're actually names for these things. So anything that is a one trial binary outcome experiment is a Bernoulli distribution. For example, binary outcome just means that there are 2 possible outcomes. The flipping of a coin is actually a Bernoulli distribution, where you have heads or tails, and you're flipping one coin one time, one trial. So that's a Bernoulli distribution. This over here, which I'm going to box over here, this is the mathematical notation for defining a Bernoulli distribution. So in Bernoulli distribution, they usually encode the outcomes as 0 or 1. So in this case, we talked about the flipping of a coin, tails is 0, heads is 1, right? Every Bernoulli distribution, you can define a probability here. And this probability will be the probability of the 1. So in this case, if I'm flipping a coin, a fair coin, P will be equal to 0.5. And the way you write it is just X squiggly line Bernoulli. BER is short for Bernoulli, probability equal to 0.5. In this case, we have a weighted coin where the probability of having a heads is 0.8. You don't have to define the probability of a tails because it is binary, because there are only 2 possible outcomes. You automatically know that if the probability of heads is 0.8, probability of tails is going to be 0.2. That's shown by this over here.
Hello? Oh, we can't hear you. No, we see our mouth moving. We can't hear you.
Can't hear you.
How about now?
Yeah, you're good.
Yes.
Sorry about that. Okay. All right. Well, where was I? Okay. So we have this biased coin where the probability of heads is 0.8. And so it is characterized with this probability mass function. So 0, the probability of getting a 0 is 0.2, probability of getting a 1 is 0.8. If we want to represent this as a cumulative distribution function, we have 0 being 0.2. And then because we're looking at values that are less than or equal to 1, the CDF value of 1 is 1. For Bernoulli distribution, the expected value is always equal to the probability itself. And then the variance, I forget the formula for the variance, but the variance will basically be actually similar to the next slide. The variance will be the probability squared, I think. Yeah, let me confirm that. Actually, let me Google that real quick. Variance of Bernoulli. So the Bernoulli should be, okay, I remember now. The variance of a Bernoulli distribution is the probability times 1 minus the probability. That's not something that you have to remember, but that's how you get 0.16 here. If you were to work out that equation that we had from a few slides ago, back here, you'll find that the variance of a Bernoulli distribution is just going to be the probability multiplied by 1 minus probability. So in this case, 0.8 times 0.2 will give you 0.16. Let me clear these drawings. Okay, so that's a Bernoulli distribution. A lot of things in life follow a Bernoulli distribution. The next one's a little bit more complicated. It's a binomial distribution, which is basically a multi-trial binary outcome experiment. So let's say we're flipping a coin multiple times. This will be characterized by a binomial distribution. So instead of just having one parameter, where here you see we have p equals 0.8, when we have a binomial distribution, and let me just circle around this. When we have a binomial distribution, we have two parameters. First, we have the probability itself, which in this case, let's just use 0.8 again. But here you also have to say how many trials. So an example of this, let's say you're playing basketball, and every time you try and make a basket, you have a 0.8 chance of getting it in the basket. So every time you shoot the ball, you have a 0.8 chance of actually getting the ball through the basket. So the way that you set up this kind of experiment, or a scenario where you would use a binomial distribution, is, okay, let's say I'm going to shoot it 3 times. What's the probability that I get in the basket 2 out of 3 times, or 1 out of 3 times, or 3 out of 3 times? So that's a binomial distribution. This might look kind of familiar or not, because this is actually a combinations formula, which was what we were doing the last study group. This formula is not important to remember, but it's good to know that if you have a 0.8 chance of making the basket and you're doing this 3 times, the probability of making it 2 times, let me just use 2 as an example. So the probability of making the basket 2 out of 3 times is, and n is 3 and k is 2. Here will be the combinations formula of 3 and 2. So the number of ways that you can choose 2 out of 3, multiplied by 0.8 is p, k is 2, and then you have 1 minus p. So in this case, this is 0.2 to the power of 1. So you work out this formula, you'll be able to get the probability. And we do have that here. So roughly the probability of making the basket 2 out of 3 times is just under 0.4. And then the probability of making the basket 3 out of 3 times is right around 0.5. So that's what a binomial distribution means. In this case, the formula for expected value and variance, again, not important to remember, but the expected value is always characterized by the number of trials multiplied by the probability. And the variance is actually the number of trials multiplied by the probability multiplied by 1 minus the probability. And that's how we get 0.48, because we have 3 times 0.8 times 0.2. Again, not important to remember, but good to know that when you're doing this kind of multi-trial binary outcome experiment, you can use a binomial distribution to model that. Okay, let's move on to talk about the normal distribution. A lot of text here, but don't worry about that for now. Normal distribution is something that we're going to be using a lot, or we're going to be using features of a normal distribution a lot as we're interpreting things like our models, or talking about our data in statistical ways. So the normal distribution is probably the one that throughout this whole presentation is the most important one to remember. So normal distributions can take many different shapes and sizes. The normal distribution is also known as the Gaussian or a bell curve. And it has a bunch of these characteristics. And we're just going to go through them one by one. And these characteristics will, as long as a distribution or a PDF looks like this, or has these characteristics, you can call it a normal distribution. So first, normal distributions are symmetric. So normal distributions are symmetric around their means. So bell curves, they're symmetric. They're the same on the left and they're mirrored on the right. the mean, median, and mode over normal distribution are equal. So in this case, if we calculate the mean in a normal distribution here, it's usually right in the middle. As you know, median also in the middle, and mode is the most common value, also in the middle. So if you have a distribution, so if you were to plot a histogram of something and it follows this kind of bell curve looking shape, the mean, median, and mode should be roughly the same. Just like any PDF, the area under the bell curve is always equal to 1. So if we have a distribution here, so let's say, we can use our movies example. So let's say we plot all the run times of movies. And I think the average, I'm just going to make up numbers. The average runtime of a movie is like 90 minutes. And then maybe on the low end, we have some outliers of I think there's some short films, so like 10 minutes. And on the high end, we have the really long, 3-hour movies. Maybe it roughly looks like, if it looks like a bell curve, it follows normal distribution. And then if you were to calculate what's the probability of a movie being between 80 to 100 minutes long, we can actually figure out what's the area under the curve and then figure out that probability there. Normal distributions are denser in the center and less dense in the tails. What that means is it is higher in the center and then lower in the tails. So these parts here are going to have low probability values. The edges here, the tail end, and in the middle, it's a higher probability value. We're going to talk about this a little bit more later, but normal distributions are defined by 2 parameters, the mean and standard deviation. So we talked about variance earlier. Standard deviation, very, very similar to variance, is actually just the square root of variance. So usually if you have a variance, you know what the standard deviation is. So defined by parameters, very similar to what I was talking about back here, where you have a binomial distribution represented by number of childhood probability. A normal distribution is defined by its mean and its standard deviation. So standard deviation is, again, just how spread out your distribution is. So some more quantitative facts about normal distributions. About 68% of the area of a normal distribution is within 1 standard deviation of the mean, and about 95% of the area is within 2 standard deviations of the mean. So that part could sound a little bit abstract. So let me just clear all of this first. So let's say we have this normal distribution here. We found the mean. Let's just say that the mean is 100. So the mean, as an example, is going to be 100. So literally the value here, this is the value of whatever whatever it is that we're measuring. Let's just go with movie run times again. So the mean movie runtime is 100 minutes. And then we calculate the standard deviation. Let's just say you can also do this through Python as well. The standard deviation of movie runtimes is 10 minutes. So what that means is if we have 100 and we go back by 1 standard deviation and front by 1 standard deviation, so the standard deviation is 10. So here, this distance is 10, same on the other side. That means that this value here is 90, and then this value here is 110. In a normal distribution, roughly, if I was to find the probability of a movie's runtime being between 90 and 110 minutes, the probability is going to be roughly 68%. That's just a fact of most normal distributions. If we have different standard deviation numbers, let's say our standard deviation was, let's say the value is more spread out. So the standard deviation, instead of being 10, let's just say maybe the standard deviation is 15. So that means this will be 85, and then this will be 115. If the standard deviation was 15, then you would say that, okay, then there's this, if I'm looking at the range of runtimes between 85 to 115, that probability would be around 68%. So it really, really depends on the mean and standard deviation. And that's how you get those rough estimates of ranges of values. The normal distribution is something that a lot of our modeling principles do come from a normal distribution. And also we will talk about that in relation to models towards the end of the phase. But for now, just knowing these rough facts, you don't have to memorize these facts at all, but just getting used to seeing the shape and how you interpret what it means by within 1 standard deviation or within 2 standard deviations. I think that could be useful. All right. So as I mentioned, normal distributions can take on many different shapes and sizes. All of these are different forms of normal distributions. So let's just take a look at these and break these down. So we have this blue, green, and red. The blue, green, and red ones are all kind of centered around 0. They're all centered around 0, meaning that their means are all 0. So you can see here this sign, which is called mu. So the mu for blue, green, and red are all 0. That means they're centered at 0. So 0 is their mean, their median, their mode. For the yellow one, the mean is 2. So you can see that the peak is actually at 2 instead of 0. Now, standard deviation is where these all differ. So the greater the standard deviation, the more spread out it is. So the more spread out it is, let's just compare the red one and the green one. So the extremes. So the green one has a standard deviation of 0.4. So with a standard deviation of 0.4, it says that 68% of the values have to be between plus minus 0.4. That's why the green looks so tall, because if I need, let me just turn this into green real quick. If I need all my values, if I need 68% of my values to be between like this range and this range, you have to have a pretty tall skinny curve for this to be 68%. This is in contrast to the red curve, which has a standard deviation of 3. So standard deviation of 3 means that 68% of my values have to be between this one and this one. So because 68% has to be in that wide range, you end up with a shorter, flatter curve, such that the area under this curve now is actually the same area as the area under the green curve that's shaded. Does that make sense? All right, so all of these are normal distributions that have different values of mu and different values of sigma, which is standard deviation. These are not important to know, the PDFs and the CDFs. These, as you can see, are pretty intense math functions. Python will do it immediately for you if you ever need to know the PDF and CDF, if you ever needed to plot this on a graph. Okay. So next we're going to talk about the standard normal distribution. So out of all the possible normal distributions, right, you can have many different combinations of means and standard deviations to have these different looking curves. What if you wanted to compare values across different normal distributions? Or what if you just want to have a measure of where a value is in relation to its distribution? We use the standard normal distribution. So standard normal distribution always has an expected value of 0 and a variance of 1. That is actually very important to remember. A standard normal distribution always has expected value of 0 and variance equal to 1. So this is a standard normal distribution, this one on the right here. Now you can actually take any normal distribution of any mean and standard deviation and transform it into a standard normal distribution. So let's just say I want to compare, let's just say that maybe there's 4 data science classes, and these are just our test scores. Flatiron School doesn't do test scores, but as an example, let's just say that these are the test scores for data science students across 4 different classes. And we have a student in each class. And let's say we want to compare, I don't know, maybe like the efficiency of the instructor that's teaching the class. So let's say we have 4 students, 1 from each class. So let's say we have, let's see, on this curve, let's say we have a student that is over, oops, let's go back. So let's say we have a student over here. We have a student over here. And we have a student over here. We have like 1 student from each class, and we just want to compare how they're doing. And because the range of values within each class and the mean and standard deviation of test scores in each class is different, we want to know how each student is doing in relation to their own class. So even though, so let's say, I don't know, scores are measured from like +, -6. So this blue class, if this person is getting a -1, how does that compare to someone in the yellow class getting a -1? This will be slightly, you want to look at them slightly differently. Let me get this orange color. There we go. Because in the blue class, if you get -1, you can see that there are a bunch of people that still did worse. But in the yellow class, if you got -1, you're at the very, very tail end because most people did here. So transforming something into the standard normal distribution allows you to compare these two folks here. So the way that you transform something from any normal distribution into a standard normal distribution is you use the Z-score formula. So Z-score, the formula is right here. And the formula we have is x minus mu divided by sigma. So let's just go back and look at our last example. Let's go back. All right, so let's use that example of like two students in those two different classes. We had, let's say we have this -1 student in the blue class, negative student in the blue class is over here. And then the -1 student in the yellow class over here. Let's figure out their Z-scores. And the Z-score formula is x minus mu divided by standard deviation. And whichever x you're using, you have to use the mu and standard deviation from that distribution. So for this yellow guy, x is -1, minus mu is 2, because here the mean is 2 and standard deviation is 0.5. So 1 minus 2 divided by 0.5, the Z-score is -6. And then for this blue guy, x is again -1 minus mu, this case the mu is 0, divided by the standard deviation of 1, we end up with -1. So this allows us to compare the two students with each other on a more similar scale. So this is basically saying the guy in the yellow class, even though they got the same score, take into consideration the distribution of the scores within their individual classes. The yellow guy actually did way worse than the blue guy because his score is -6, whereas the blue guy's score is -1. So this allows us to compare scores across different distributions. A Z-score is also helpful to put into perspective how far away that particular score is from the mean. So another way to interpret Z-score is Z-score is literally the number of standard deviations you are away from the mean. So remember how standard deviation, again, is a particular number that we had. So happens that this blue one is a standard normal distribution as well. So this blue guy is 1 standard deviation less than the average in the class, whereas the yellow guy was 6 standard deviations less than the average in the class. So you can actually work this out. The average in this yellow class was 2, and the standard deviation was 0.5. So 6 standard deviations is 3. So they were 6 standard deviations less because 2 minus 3 gives you -1. So that's another way to interpret it. It just allows you to compare just relative to their individual classes. How is each student doing? All right. One last slide. So this kind of sums up what I was saying earlier. A Z-score tells us how many standard deviations away from a mean point, from the mean a point would be in a standard normal distribution. You can also look up the probability associated with every Z-score, and this will be relevant for our next study group. You can actually use this Z table. So let's just say for those students back there, we wanted to see this blue student who was at -1. What's the probability of a student in that class getting less than that guy? It would be the area. Let me just draw that out real quick. It would be the area under here. This rough blue area will be the probability of someone scoring lower than that guy. In the yellow scenario, we have -1 over here. Let's see, the 0 line is there. So there's like a very, very small probability, very small probability that someone did worse than that guy. So that's another way to compare. And we'll talk about that later. Basically, if you want to find this exact, area, you can use the Z-score table. Oops, let me delete those scribbles. Okay, so how you use the Z-score table is you use the Z-score. So we had that Z-score of -1 for the blue guy. And the way that you read the Z-score table, it goes up to 2 decimal places for Z-score. So here's -1.00. The probability of someone doing worse is this value here. The probability of someone doing worse is 0.1587. As you can see, the Z-score table doesn't go smaller than -3.49. So you can pretty much assume that there's almost a 0 probability that someone did worse in the yellow class than that one guy in that yellow class. If that makes sense. Because you see how earlier that area under the curve was almost nothing. That's just saying that for that guy in that class, there is a very small chance that someone did worse than him. All right, and we'll talk more about using the Z table in the context of conducting statistical tests on Wednesday at our next study group. But yeah, I know that was a lot of stats theory. I would say take some time to digest, maybe watch some of the other videos that I put up, the central lecture videos that I put up on the curriculum, maybe work through some of the labs. Statistics is like maybe 2 semesters of college worth of material. So it's a lot, and I understand it's super technical. For our purposes, we will be talking about stats in relation to models. And in our models, some of these concepts will come back. So it is important to like roughly know what's going on, but not important to memorize all these definitions. I do want to really, really highlight that before we end off. But yeah, this is the last slide. Does anyone have any questions?
What does the mu stand for again? What does it represent?
The mu stands for the mean of that normal distribution. So whatever the value is for the peak here. So mu equals 2. That means the peak here for this yellow guy is 2.
Okay. All right. Thank you.
You're welcome.
I can't think. Oh, excuse me. I can't think of a reason, but is there any reason why you would keep not normalized distribution if you had, let's say you had like, one thing I can think of is like 3-dimensional or like another dimension of data? Would that ever affect it would affect obviously distribution, but like how would you go about that?
That's actually something that we'll be doing at the end of this phase, like normalizing some, let's say you have like movie runtime, profit, budget, all of these things, and you wanted to like relate them. Interestingly enough, let's just say that we have a curve that looks almost normal. Let's just say that, okay, let me use a different color. Let's use this color. Okay, so let's just say that we have a curve that it's kind of normal, but nothing is ever like perfectly normal. So let's just say we have this line here. If we were to convert it to a normal distribution, a standard normal distribution, I mean, the overall shape of this actually will not change very much. It will just be squished a little such that it matches, and recentered such that it matches the features of a standard normal distribution. So the shape of the curve itself actually will not change. This is very interesting. But yes, the relationship between variables will change. So let's say that, I guess hard to say without a bunch of like concrete examples, but
I just kind of that's a good enough answer. I'm just kind of curious about like multi-dimensional and like a normal distribution under like multivariate data. So
yeah, for sure. So I remember you in your project you did Pearson correlation, right?
Yeah.
So if you understand Pearson correlation, if you were to do the Pearson correlation between 2 variables, and then you scale one of them but not the other, the Pearson correlation actually remains the same.
So that makes sense actually.
Yeah.
That makes sense.
Yeah.
Okay.
We'll get more into details. There's a lot here, and I know the order is a bit different from how you would traditionally do a statistics course, but it's really to just hit on the main things that will come back for our actual data science work in like 3-4 weeks.
Okay, sounds good.
All right. Anything else? Cool. I'll stop the recording here.